Hello, and welcome to 5 Minute Math. Today we are looking at the 7th grade concept of simple and compound probabilities. This is 7.6i Readiness Practice, the Proficient version. If you're interested in exploring the 7.6i Readiness Practice for the intermediate or advanced versions, or the Readiness Practice resource aligned with any other standard, you can find those by using the link in the video description. So we are flipping a coin, and it's a fair coin, which means it's got one heads, one tails. That's all that means. It's not a trick coin. It's not weighted heavily on one side over another side. Nothing like that. So it's a legit coin. It's got two options, right? We've got a heads, we have a tails. Now, the experiment resulted in 12 heads and 8 tails out of 20 flips. So we need to think about two different types of probabilities, a theoretical probability and an experimental probability, okay? So the theoretical probability is what, and we've got a key word here that's going to be different for each of these, what should happen. So I'm going to underline that because a theoretical probability is if everything is equal and everything is fair, what should happen. Experimental is different. It's what, let's see if I can spell that right. What did happen? So that's the difference. Experimental is, okay, I did the experiment. I know what should have happened, what actually happened. So theoretical probability on a single flip is, well, how many heads are there? There's one heads. How many options are there? Well, there's one heads out of two options. So, right, our probability is 1 out of 2, 1/2. That's your probability of flipping a heads theoretically. Now, what actually happened? Well, how many heads did we get? Well, we've got 12 heads out of how many total flips? 20, right? So we're going to show it as a fraction where our numerator is our number of results. Our denominator is the total number of tries or attempts. And so we can kind of show that right here. Results over attempts is going to be our experimental. So that's the difference here is this is experimental. Now we need to simplify this, right? So we can make that, if we divide by half, right, we're going to get 6/10. We divide by half again, we're going to get 3/5. Or you could have just divided by 4 and got straight to 3/5. But we have about a 3/5, which is larger than 1/2 experimental probability of getting the heads, because experimental probability doesn't always land up the same way that theoretical probability is, random chance. All right, problem 2, we're taking multiple choice quiz, and for Q1, right, we've got 3 choices, right? We've got A, we've got B, and we've got C. And then for question 2, we've got 3 choices. And to make them slightly different, we're going to do W, X, Y, and Z. Now, if we're just randomly guessing, right, what is the theoretical probability that student answers the first question correctly and the second question incorrectly? Okay, well, so we need to get this correct, and then we need to get this incorrect. Now, first, let's draw a tree diagram, okay? So what we want to do here is we want to show all the possible choices. And so let's start with our first event, because this is a compound event, because there's two simple events kind of stacked together. So let's do it like this. If our Q1 is A, what are all the ways that we could do Q2? Well, it could be A, and then you get a W, right? A, and then you get an X, A, and then you get a Y, A, and then you get a Z. So if you choose A first, those are your only 4 choices. And then I can repeat the same thing with B. You can get B and then W, B and then X, B and then Y, B and then Z. So we've shown you with the tree diagram all the different possibilities with A, different possibilities with B. Let's go ahead and do C. W, X, Y, Z. Now, that's our first one right here. So we'll put tree diagram here. So that's clear on our answer key. Now let's look at our probability. I want to get A, B, or C on problem 1, and I need to get it correct. Okay, well, how many correct answers are there? Well, there's one correct answer. And how many choices are there? There are 3 choices. Okay. Now, if I want to get the second question incorrect, this is a multiple choice problem, so there's one correct answer. So how many incorrect choices are there? Well, I've got 3 incorrect choices, and then I've got 4 possible answers. So I'm obviously much more likely to get an incorrect answer on question 2 than I am to get a correct answer on question 1. So if we want to do first correct, second incorrect, I'm going to take my choices from question 1, my 1/3, my probability, and I'm going to multiply that by my probability of getting the incorrect answer on the next one. So that's going to be 3 12. So if you just multiply straight across, and that's going to be our answer on that. Now that if we think about it, that makes sense, right? So we could do that with our tree diagram. Okay, so let's say that I'm going to choose a correct answer for both. Okay, so if I'm wanting to get the correct answer on the question 1 and incorrect on question 2, right? I've selected just randomly B and Y. So here's my correct path right here. Well, how many choices? I got 12 choices over here on Q2. So you see I got my 12 right here. How many choices are there that are correct on 1? So that's B, incorrect on 2. Well, look, here are my 3 incorrect choices. I could have done this, I could have done this, and I could have done this. They all would have had the first one correct, but they would have had the second one incorrect. So you could do that mathematically. You could also do that with your tree diagram, and you can just look at the number of choices and say, well, there's 3 out of 12 that have question 1 correct and question 2 incorrect. And then finally on number 3, we've got a jar. We got 3 red, 2 blue, and 5 green. So let's draw that. I'm going to get you 3 red, 2 blue, and then how many green? 5 green. 1, 2, 3, 4, 5. All right, so here's my jar. Now, one marble is drawn, replaced, and then another marble is drawn. So it's important to grab one, put it back, and then grab another one. It's another compound event because I've got 2 simple events. If we didn't replace it, then the denominator would change for the second one. If we kept that first one out, then my total number of possible choices would have dropped. So the theoretical probability of drawing a red, then a blue. Okay, so we're going to do a red and then a blue. Well, what is my probability of choosing a red? Well, I've got 3 reds out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, I've got 10 choices. So 3 out of 10. I'm going to put the first one back. I'm going to pull out a second one. What's my probability of getting a blue? Well, I've got 2 out of 10. Or if we want to, we can simplify that. We can do 1/5. And simplifying will help because I'm going to have to multiply anyways. So if the experiment is repeated 50 times, and the outcome occurred 4 times, what is the experimental probability? And so you see we're looking at the experimental probability and the theoretical probability. So let's do the theoretical first. All right, so that's going to be your 3/10 times your 1/5, and that's going to get 3/50. So you have a 3 out of 50 chance. It would have been 6 out of 100, but then we would have had to simplify to theoretically choose a red than a blue. Not very high. Now, your experimental is going to be a little bit easier because we're just reporting what we see. It happened 4 times. And how many tries did it take to get that 4 times? 50. So you see they're very close. But they're not always going to match because you have a little bit of RNG. You got a little bit of randomness thrown in there. So if you're interested in exploring the 7.6i Readiness Practice Resource for the intermediate or advanced version, or the Readiness Practice Resource along with any other standard, you could find those by using the link in the video description.